The discovery of neuropods, specialized gut cells that communicate directly with the brain, has opened a bold new chapter in the science of satiety, one that could radically transform how we understand and treat overeating. For decades, efforts to combat obesity and metabolic disorders have focused on willpower, calorie counting, or pharmaceutical appetite suppressants. But what if the key to healthier eating isn't in the mind, but in the gut's own built-in neural circuitry? Neuropods represent a direct biological interface between food, gut, and brain, capable of sensing nutrients and relaying information about fullness in milliseconds. As our understanding of these cells deepens, so does the possibility of leveraging them to naturally regulate appetite, reduce portion sizes, and reset metabolic balance without the side effects of current interventions. Unlike most gut cells, neuropods are not passive participants in digestion. They form synapse-like connections with afferent fibers of the vagus nerve, meaning they can trigger neural signals that reach the brainstem and influence perception of hunger or satiety before the body even finishes digesting food. They respond to specific nutrients, especially sugars, amino acids, and fatty acids, and release fast-acting neurotransmitters like glutamate, ADP, and serotonin, which send real-time feedback to brain centers responsible for meal termination and energy regulation. What makes this system so promising is its speed, specificity, and precision. Rather than relying on delayed hormonal cues like leptin or insulin, neuropods can offer a minute-by-minute update on the nutrient status of the gut. This opens a new frontier for clinical innovation. If we can identify the exact nutrient combinations or microbial signals that optimize neuropod activation, we might be able to design satiety-enhancing meals or supplements that make people feel full with less food. Already, early studies suggest that prebiotics, fermentable fibers, and certain amino acids increase neuropod activity and vagal firing rates. Similarly, short-chain fatty acids, SCFAs, produced by gut microbes, like butyrate and propionate, appear to sensitize neuropods and enhance their satiety signaling. This implies a future where food is not just nutritious or calorie-controlled, but neurologically tuned to activate the body's own braking system for appetite. The potential doesn't stop at dietary formulation. Pharmaceutical research is now exploring ways to target neuropods directly using nutrient-mimetic compounds, or gut-safe neural modulators. Instead of stimulating dopamine pathways in the brain, as many weight loss drugs do, with addictive risks, these therapies would activate vagal signaling through the gut, creating a more physiological sense of fullness. This could lead to fewer cravings, smaller portions, and sustainable weight control, without the typical rebound effect. For individuals struggling with compulsive eating, this approach could help reestablish an internal sense of when enough is enough, something often blunted by processed diets and chronic stress. Another promising direction is using personalized microbiome interventions to enhance neuropod responsiveness. Because gut microbes can influence neuropod function by producing or blocking certain neurotransmitters or modulating local inflammation, it may be possible to use precision probiotics or engineered bacterial strains to optimize the gut-brain communication that controls satiety. Imagine a probiotic not just for digestion or immunity, but to amplify the feeling of satisfaction after a balanced meal. It's also worth noting the safety and elegance of targeting this system. Unlike bariatric surgery or stimulant-based weight loss drugs, neuropod-based interventions would work with the body's natural biology, not against it. They wouldn't block hunger altogether, which often leads to malnutrition or mood disorders, but would restore the lost sensitivity of satiety, a biological compass that has been dulled by hyperpalatable foods and erratic eating schedules. For people living with obesity, metabolic syndrome, or even type 2 diabetes, this could provide a grounded, sustainable path back to homeostasis. Of course, there is much left to learn. We still don't fully understand how neuropods integrate multiple types of nutrient signals, or how they might behave differently in obese versus lean individuals. It's also unclear how this system adapts, or desensitizes, under chronic exposure to high-fat, high-sugar diets. But what's emerging is a clear, compelling truth. The gut has a voice, and it speaks not only to the immune system and the microbes around it, but directly to the brain's appetite and reward centers. By learning to listen and eventually to modulate this voice, we may gain a powerful, biologically intuitive new tool for tackling overeating and restoring metabolic health.